So we understand what parallax is, what it indicates as far as the relative differences in elevation when we're talking about aerial photography. We're going to progress now towards what we do with it and how we can measure it. The first thing we need to understand is the concept of the floating mark. Here again, we're going to go back to those that transparent medium placed in front of what we're viewing. In this case, it could be that we're actually viewing the photos. But what we have here is two marks are going to be introduced into the optical axis of each viewpoint. Um, One mark on each of the axis. Then, when they're viewed together, the points are going to appear as one object at a certain distance from the viewpoint, at a certain elevation. So, in other words, if I'm looking at this photograph and there's something on the ground at point C, and I was to take a measuring mark, just let's say a red dot, and place that red dot in each photo system, so that as I looked through it in stereo, I saw this red dot right where point C is in the left photo and right where point C is in the right photo. Then that red dot would appear as one object. As long as I was focused on C, it would appear as one object, and it would appear as the same distance, the same height as point C. And kind of illustrate this, if you were to take two pencils and hold them at arm's length and look at something off in the distance, and then move the pencils either closer to each other or farther away, so that the right pencil blocks the view of the object in the right eye, and the left pencil blocks the view of the object in the left eye. So you're looking at something about 50 feet away, the corner of a cabinet, and the right pencil eraser is going to cover the corner of the cabinet for the right eye. The left eraser is going to cover the corner of the cabinet for the left eye. Those pencils are a certain distance apart. If I was to look at something much closer, the corner of a table that's only a third of the distance away, now what I would find is that those erasers are too far apart. I have to move them closer together if I want to cover whatever that object is that's closer. And the closer I come, the closer they get together, because that parallactic angle is changing. If I can introduce something like that into the measurement system, into this three-dimensional viewing system, then those dots, in essence, are measuring the parallax as they measure the parallactic angle. So that's the idea of the floating mark. At some point, we'll take a stereoscope and make a simple measuring mark with just ink dots on a clear acetate film, and be able to move those dots around in that three-dimensional space and actually see the differences in the position on the photo. Well, as we go along as far as lines of accuracy, if we take a mirror stereoscope and what is called a parallax bar, it's a very precise instrument. I line up the photos so that I'm seeing them in stereo. They're taped down so that they're not going to move. They're rotated so that the axes are lined up and I know this because I don't have any Y parallax, then I can take that parallax bar, and it has a glass plate with measuring marks scribed on it. I'd put the measuring mark on the same object in both photos, and those very precise calipers would measure the parallax between the two photos. It's almost like the one where we talked about taping it down and measuring it with just measuring it with a ruler. Well, this is going to be able to measure very precisely differences in parallax between objects in the photos. Because at some point, it's not just the parallax for each point, it's the difference in parallaxes between two different points. To be able to say that there is more or less parallax for one point than another, indicating then that one point is higher than another based on their relative measurements. And finally, like everything else, if there's a simple way to do it, if there's a physical way, a mechanical way, then certainly there's a mathematical way. Well, actually, the math doesn't have anything to do with making the measurements. It has to do with using the measurements. And what we're going to look at now are known as parallax equations, things that we can do once we have parallax. Once we have the measured parallax. We talked before about making an arbitrary ground coordinate system within one photo, and that was simply by taking the x and y in that photo and scaling it. We scale the x, we scale the y, and we get an arbitrary ground coordinate system that could be transformed then if we wanted to. In the same way, if I set up a coordinate system and call 0, 0 as the principal point of the left photo, then I can make a measurement in that new coordinate system for a new point. Let's call it A. I have that little x is the coordinate system based on the flight line, an x for that point, 0, 0 at the left principal point. I have a parallax measurement for point A, and I have a photo base. In other words, how far apart were the cameras when it was imaged? Now, there's ways to get the base, but in this equation, let's just say that we have it. So we take the photo base, multiply it by the ratio of the x-coordinate for point A divided by the parallax, and that's going to give me this arbitrary x for point A, an arbitrary ground x for point A. In essence, we're scaling it, but taking into account the parallax, because different points are going to have different parallax. And if we did this for multiple points, things would start to build in their three-dimensional geometric positions. Same thing with y. I take the y in the flight line axis, divide it by the parallax for the given point, multiply it by the photo base, and I've got the arbitrary y. So I could begin to build this arbitrary coordinate system based on parallax and photo base. Well, if I have a control point, where I have the elevation of something, I can even start to get elevations or height differences based on that control point. Now I can get height variations in any case, but I've got a control point that I can start to relate them to something on the ground. Any 2 points are going to have two different parallaxes. Okay, point A has a parallax number. It's just some millimeters that change between the left photo and the right photo. There is a parallax for control point C. If I take the parallax for A and the parallax for C, subtract parallax C from parallax A, I've got a delta parallax. Well, once I've got the delta parallax, a lot of these other things are given. The height of C, okay, remember that's a control point, so we know the height of C. We know that big H, what is big H? It's the height MSL. It's the flying height over the datum. We've got that from the flight report. We've got the height of C from the control report. We've got the parallax, the delta parallax that we just computed, just taking the two numbers in millimeters, subtracting one from the other, getting a delta P, and then the parallax for A, that was one of the givens. So if we plug in elevation of C, delta parallax, height above datum, height above datum for the control point, and that is what its height is. H for point C is its height above the datum. Plug in the parallax for A, and what we're going to get is an approximate height for point A. Now, once again, we can set the datum at any given point and come up with delta elevations. You know, if instead of a control point, we just put the bottom of the pole, you know, that we could plug that in all these places and come up with a height of a pole based on the datum being the bottom. To make all of these calculations, it is necessary to know both the flying height and the air base, that base distance between the cameras. If either of them are known, and you know, most often that's going to be the height above the datum, you know, from the altimeter, and at least one control point is visible in the overlap area, then the other number could be computed, you know, by rearranging the parallax equation. The flying height or base can be computed, and it all goes back to the ratios and those triangles and everything being scaling from there. The big H is the height above the datum. The little h is the height of that control point that falls inside the overlap area. The B is the photo base. P is the parallax for the point in question. F is focal length. Everything except for one of those numbers would be given, and you just plug everything in, and out would come the other number, and then it could be used in the calculations. These calculations are not the kind of thing that you do by hand very often, really ever, but it's what the instrumentation and what the measurements are actually reflecting for every single measurement that's made in a photogrammetric system. And we probably will do at least one of these calculations to compare it to the vertical photo calculations, so that we can see how things compare in that way.